So hello everyone, I am Sayan Mandal. Today I am going to present a paper StarCDN, which is Moving Content Delivery Network to Space. This paper was published on the proceedings of ACM SICOM 2025 conference. So before deep diving into the paper, let's understand what are CDNs. So content delivery networks caches and serve the content from edge server located close to end users to reduce latency, to save the backbone bandwidth, and to improve the reliability at scale. So if we see the real data, so these CDNs serves an estimated of 75% of all internet traffic today, and this includes web pages, video streaming, and software downloads, and many other things. So basically, if all the data comes from the data center, so it will have a long round trip time, so it will add to the latency and will give a very bad user experience. So for that we use CDNs to cache and to use it as a proxy server so that the user experience becomes smooth. So these are basically the CDNs. But if I talk about the satellite internet today, but satellite internet work in a bit different way. So this idea of CDN, or the idea of caching the content in some proxy server, is not that easy in case of satellite, because it comes with some limitations. So if I see about the problems with the current system, so the first problem is that about high latency. So this ground routing adds an approximate of 100 milliseconds of avoidable delay on the top of the inherited satellite round trip time. Okay, so this problem of latency arises because of this bent pipe architecture. So you can see that whenever user request something by using the internet which is provided by some satellite provider, like let's say Starlink, so that request from user goes to satellite, and that content again goes to the ground station, and from ground station it gets the content from the nearby CDN server or the internet, and then it again sent back to the satellite and again reaches to the user. Okay, and why this problem arises? Because our existing satellite architecture don't support any kind of caching. Okay, so since satellite do not support caching or to process the content, so this becomes a huge bottleneck for content delivery networks to work in this satellite domain. And also every user request needs to touch the earth's surface, which adds a ground infrastructure, and it increases the cost. Okay, so if the same movie, let's say, is watched by 100 people, then that same movie content will be uploaded from ground 100 times and will be sent back to the user, because those satellites are not capable of neither caching nor processing. So there will be a huge inefficient routing involved. So these are the main problem with the current CDN infrastructure with the satellite internet. So this paper try to solve this issue. This paper try to make sure that this CDN also works in satellite as well by introducing the cache. But only introducing the cache won't make sense because of some reason. So here yeah, so before I move into the reasons, I just want to discuss about the bandwidth bottleneck, which is that, so there are satellites in the space, so those satellites can interact with each other, can share the data, and those type of satellite to satellite link is known as ISL, that is inter satellite link, and the ground to satellite link is known as uplink. Okay, so if I see the real means based on our current infrastructure, so this uplink bandwidth is around 20 Gbps, where this inter satellite link works at 100 Gbps per second. So you can see that this ground to satellite uplink adds a huge bottleneck for this CDN to work at the satellite level. So now comes that only simply introducing the cache. So the most intuitive solution that might come is that we can simply add the caching on the satellites, then our problem will be solved. But that is not the a good way. Instead, we cannot scale that, because those satellites are not capable of carrying very huge loads, because the weight constraint is there. So we just cannot keep on increasing the cache size on the satellite. So we have to use cache, but in some intelligent manner. So those solutions, so if I talk about the key challenges that we have, the thing is that those satellite continuously revolves around the earth with a time interval of 90 minutes. Okay, so those satellites are not fixed, right? So currently some satellite is serving the Europe, and after a few minutes it may serve some other place, maybe America, right? So this coverage, so rapid shifting of coverage is there. And also the traditional CDN assumption break. So like traditional CDNs assume that edge location with predictable user population, but this thing neither holds in this lower earth orbit satellite environment, right? So these CDNs are not still. So simply caching, if we, let's say for example, if there is a possibility of let's say introducing infinite cache, since this will not scale, because the coverage is not fixed, it continuously moves on changing, and the central assumption behind CDN, it actually breaks. So that's the main reason simply caching can increase the problems a bit, means can solve these problems a bit but cannot scale much. Okay, so that's why we need to come with some uh, optimized methods to solve this problem. So so the one problem is that since I said that there is a coverage issue. Okay, so at the time suppose the satellite is serving the US region, and then suddenly after few minutes it starts serving the US people. Okay, sorry, the Europe people, right? So and so if at time instance t1 the satellite is serving US, and let's say some contents are being watched by some people of US, and those contents are getting cached in the satellite. But when that satellite will move to Europe, then those Europe people will have a different demand. Maybe those content will be different from the content the people watch from US, right? So the cached content may become useless. Okay, so almost immediately. So you cache for a particular region, then the satellite moves, and some new satellite comes, then that caching becomes useless. Okay, so this is a dynamic content problem, and this is known as overlap. Like what fraction of the content is same between US and Europe, so that is known as the overlap. Okay, so very low overlap exists. So the NAPE solution, which I have already talked about, is that simply introduce a cache, and you may use this LRU cache policy like least recently used, like for the eviction purpose obviously. So this is very simple to implement, but as I told, it is definitely fundamentally broken at scale, because it achieves a very low hit rate because of this continuous movement of the satellites. So this independent cache means if we introduce this LRU, so this independent cache achieves a less than 60% hit rate, and the satellites don't share the knowledge of what it has already cached by nearby. Okay, so in this NAPE approach, there is no mechanism by which those satellites can transfer their cache information to other. So and the second issue is of the redundant storage, because at a time at a same place you can access 10 different satellites. Okay, so you can, so this if I talk about the Starlink, it has some kind of scheduler that maps an user with a particular satellite depending on that region. So at a time those scheduler can map us between any of those 10 satellites, right? So if two people are watching the same movie sitting in the same place or the same region obviously, then those two may be connected on two different satellites, because of which the same content need to be cached on both the satellites. And this dynamic mapping of the user to the satellite is not in our hand. It happens in some random manner or in some algorithm that we cannot control, so it is not in our hand. So there is an issue of redundant storage, and also this motion blindness, that is this LRU has conceptual of orbital movement, so it cannot anticipate the audience a satellite is about to serve. So these are the mainly the three major reasons why the NAPE solution of installing the cache on the satellite fails. So the main idea of this StarCDN is that we of course install the in-space caching, that is the contents are stored from the satellites, not ground servers. Actually we install the cache, but we do it in some intelligent manner so that we can overcome these limitations or these failure regions. Okay, so we use this ISL routing, that is inter satellite link transmission. So we used to transmit the content from one satellite to other, because those inter satellite links works at a much higher scale of 100 Gbps compared to the ground one. It works with only 20 Gbps. So rather than caching, means again fetching the content from ground, we fetch the content from nearby satellites, because those links are quite fast of around 100 Gbps. So this obviously because of doing this, since we are not going to the ground, so this extra 100 milliseconds of this grounding penalty get reduced. And also there is uplink saving, since those contents are not repeatedly fetched from the ground, so that bandwidth is getting saved, and so drastically reduces the cost. So these are the main idea. Now I will explain that how this idea were actually implemented in this StarCDN paper in my subsequent slides. So till now we have seen the core ideas behind this StarCDNs. Now we will see the main ideas that were used to implement this in this paper StarCDN. So the first algorithm which comes is of consistent hashing. So it actually split the contents into k buckets, and this value of k is a hyperparameter that we need to fix a particular value so that we will get the maximum benefit, and how to choose that value we will come later. But for now, let's say we split the content into k buckets, and each bucket is mapped to a particular satellite, which is decided by the hash function. That's why it is known as the consistent hashing. Okay, and okay, so in this way we are so why this consistent hashing? So by deterministically mapping each content bucket to a specific satellite, StarCDN ensures every piece of content has exactly one home, or exactly one copy in the constellation at any time. So by doing this we are avoiding redundancy, so there is no redundancy. Each item is cached once across the fleet, and better utilization. The storage is spread evenly, and predictable routing, obviously, since it is done by an hash function. So we actually know that where the particular part of an content resides by just simply looking at the bucket name or the bucket address. So this is quite of predictable routing kind of a thing. Now comes how this actually works. So let's say I have one example also, so I will take this. So let's say in this example you can see this 6 satellites which are colored. So this green one and green one, so this N1 and N3 comprises of one bucket, S1 S3 is the second bucket, and this H2 is the third bucket, and about this N2 is the fourth bucket. So there are 4 buckets you can see, okay. And obviously there is redundancy but less, okay, because since there are a problem of localization, or means that temporal locality is there. So let's say in this particular region these 4 satellites are serving a particular region. So you can see that there are 4 buckets, and those 4 buckets are mapped into 4 different satellites, okay. So when an request comes, let's say one user want to access the content which was stored in this orange bucket, and he luckily connects to this orange satellite only, then it's the cache hit, or you can say that, yeah, so it is the cache hit. So the content will be directly served from this orange bucket to the user. But let's say that user get maps to a different satellite, let's say this pink one, then there will be a cache miss. So it will try to, since it already has the hash function, it will get to know that which satellite have that particular content. So it will simply forward the request to N2, so that N2 can serve that user via this S2, okay. So in this way this consistent hashing works. So I have already written here. So that is user connects, that is a client links to the nearest satellite, then it checks its cache and inspect the local satellite cache, and then route to peer, like forward the request to the correct satellite. If that is not the correct satellite, then, but if still it is not found, then we can obviously go to ground and fetch the data, right. So in this way this consistent hashing works. So you can see that each hop is designed to minimize latency. So ground fetches are the last resort, triggered only when the constellations cannot serve the content locally, okay. So let's say I have a huge content, I divide it into k parts, but those k buckets and obviously each bucket will have some capacity. Let's say I have 4 buckets, so I can at most store 4 times k amount of content, but I have a very huge content, so all those content cannot be stored in those four buckets, right. So in that case we go to ground and fetch, and we can use this LRU policy, fine. So in this way we use the idea of consistent hashing. And so one idea might come is that, so to solve this problem we just simply increase the value of k. Yeah, that will work, but that will increase the cost in routing, because if the k is more, so this routing there will be multiple hops within the satellite only, okay. So this inter-routing cost will get increased if we increase the value of k, and also if we increase the value of k, the cache hit will increase. So cache hitting, increasing it is good, but increasing the latency within the routing is a bad thing. So there is a trade-off between the value of k and the latency, or the routing latency, and those trade-off I will come in the later slide. So this first optimization is about consistent hashing that I have already cleared. Now comes to the second optimization, which is about the relate fetch, right. So I will come to the figure, and I will try to explain. So the thing is that relate fetch, okay. So let's say this four I hope you can see the annotation. So this N2, N3, S3, S2, these 4 are serving at a particular place, right. And since they are moving with a very high speed, around 8 km per second, so after a few minutes this 4 satellite will shift to this right, okay. So this 4 satellite will go here, and these 2 will come here, right. So what will happen, these 2 satellite will go there, and these 2 will come here. So suppose in that case, if there is a cache miss, so instead of going to ground, we can simply ask the nearest satellite, because they were present just before few minutes ago, so they might have those content cached. So rather than, so if there is a cache missed in the bucket, then rather than going to the ground, we can simply ask the neighboring satellites which were just present few minutes back, and those might be a very good candidate of solving the cache miss problem, because they will have a very high probability of getting those contents in those satellites, because they have already served that region few minutes back, okay. So this is known as the relate fetch. So this obviously works opposite to the flow of the satellite motion. So if the satellite is moving in this way, like from left to right, then the data flow will have from right to left, okay, will have from right to left. So I have actually written it in a very nice way. So relate fetch, that is pulling data across the constellation. So when a satellite misses in its local cache, it doesn't immediately fall back to the ground. Instead it queries a neighboring satellite over the inter-satellite link. So these things is triggered on cache miss. So this relate fetch only activates when the local cache serves the request and keeping the bandwidth to use reactive and not speculative. So one thing. So one a question that might arise is that, so before leaving the satellite a particular place, it may uh, transfer every content to its nearest satellite, because that satellite is going to take over his position. But that will be prefetching. But this is not a good idea, because some unnecessary content might get transferred, which will increase the bandwidth, and it will increase the latency. Okay, so it will waste the bandwidth. So we don't do the prefetch, we rather do a reactive fetch. So if there is a miss, then only we try to transfer that content. Okay, so there is no prefetching content. So it is not like that every content from the neighboring satellite moves to the current space. It is not like that. Only the content which is needed, that information get transferred. And why this is a good choice? Because of this inter satellite links. So this high speed ISLs connect adjacent satellite, enabling sub millisecond data relay without touching the ground. Okay, so we are using this neighboring satellite as a source. So so this backward flow, as I already said, like these satellites continuously move forward their orbit, but StarCDN deliberately routes the cached content in the opposite direction. Because the satellite is ahead, already served the ground user at a given region, so it caches, so its caches are warm and relevant. So flowing the content backward to the approaching satellite means it arrived preloaded for the users about the passover, right? So this directional asymmetry is what makes the StarCDN cache reuse significantly more effective than the NAV LRU approach. So these are the two optimization which are done. So obviously, as I said, that why not prefetch? Because the demand is unpredictable, but there will be bandwidth waste, and obviously storage pressure, because the satellite have very limited capacity. So relate fetch is reactive, not proactive. So the architecture already explained. So now the time has come for the evaluation. So we do a simulation where we use around 1170 satellites. We use the trace of 5 days, and we do 2 billion requests over a data volume of 2.5 petabyte. And we generate this, and also this is very difficult to evaluate this kind of architecture, because since the satellites are moving and it will be very difficult to evaluate, so we actually generate the synthetic data which are pretty close to the real life internet data, and using those we evaluate this model. So now coming to the cache hit rate result. So if we use the simple LRU without hashing or this relay fetch, then the cache hit will be around 60%, and if we use only hashing, then it increases to 66%, and if we are using both hashing and the relay fetch, then we are improving the cache hit rate by 71%. Okay, so there is a 18% of relative improvement by using this StarCDN techniques. So this every additional percent point of hit rate eliminates millions of ground prefetches per day across the constellation. So these are the results which are taken from the paper. We can see that this lowermost curve is of the base case, or the simple LRU, and the topmost curve is the ideal one. So actually it assumes that the satellites are static. So if they are static, then they are capable of giving the ideal case scenarios. But since that is not the possible, that is the ideal case, because the satellite have to revolve continuously around that to stay that in that position. So this ideal case is not possible, but though that ideal case we use as a upper limit, and we check that how much we can reach closer to that ideal. Okay, so this topmost is about the ideal, and the this bottommost red dot is about the simple normal LRU, and this green one is the StarCDN one, and this two and the bottom two lines are simply using StarCDN with only hashing, and using StarCDN with only this prefetch or the relay fetch, and the green one is a combination of both. So you can see that if we these experiments were done. So this request hit rate versus cache size, and this is byte hit rate versus cache size. So you can see that the nature of graph is almost same. And also one small observation you can see between if we increase the value of k, that is if we increase the number of bucket, then from 4 to 9, then you can see that by doing this the hit rate obviously increases, but not that much, because it actually comes with the cost of the routing. Okay, so this is about means the comparison between, means if we increase the value of k, how the rates are getting changed is shown in the figure 7. Now in the figure 12, for two different type of traffic, how the behavior is there. So for simply web traffic, we can see that the performance is nearly same in case of StarCDN compared to the baseline one. There is not much difference, but in case of the download traffic, that this difference is significant, obviously, because for the small traffic, like the small web traffic, those traffics are actually very small and short lived. So for them this cache doesn't improve much by using the cache size, but for huge download, like for data heavy application, by increasing the cache size obviously improves my hit rate. Okay, so these are the two observations that we can see from the paper. So if we talk about the bandwidth saving, so by using this star CDN, we are avoiding this ground to satellite data transfer. So if there is no cache and we take it as a baseline, okay, then as compared to no cache, this LRU achieves 32 times, and sorry, means if the no cache scenario takes 100 Gbps of uplink, then this LRU will take 32 Gbps and this star CDN will take 22 Gbps. So we can see that there is up to 80% bandwidth reduction by introducing the idea of star CDN. So this star CDN reduces the bandwidth by approximately 80%. Okay, so obviously you can see from this graph taken from the paper, so you can see that when you are increasing the cache size, how this uplink percentage is getting affected depending on the model we are using. So, and this behavior is more or less same when we are increasing the cache size, okay, and it actually remains almost same. There is not much a difference, because obviously there is a trade-off between this cache size and latency. If we increase the cache size, obviously the head rate will increase, but on the other hand, because of the routing, the latency will increase. Okay, so yeah, so that's the main idea I was talking about. So the latency improvement, so as compared to the baseline of 55 milliseconds, so with normal cache we can achieve a latency of 55 milliseconds, but if we use star CDN, then this latency reduces to 22 milliseconds. So this star CDN delivers approximately 2.5 times faster response as compared to the baseline latency. So this is the main trade-off which I was talking about. So this balancing head rate versus routing overhead is an issue. So this increasing k, or the number of consistent hash bucket, this improves the cache head rate by distributing the content more precisely, but it adds routing hops and latency. So this k equal to 4 or 9 sits the sweet spots, like it meaningfully hit rate gains without prohibiting the routing overhead. Okay, so if we go the value of k beyond 9, then this marginal head rate gains are overweighted by the latency cost of the additional routing steps. So here are the two graphs. You can see that this is about the routing latency. So if we increase k, the routing latency get increased, which is actually bad. But if we increase the k, the cache hit rate should also increase, which is a good one. Okay, so there is always a trade-off between this routing latency and cache hit rate. So now coming to the conclusion part, the first CDN built for space. So the star CDN demonstrates that content delivery network is not just a terrestrial problem, and that orbital mechanics can be turned into a caching advantage. So we are using the advantages of the locality. That means the satellite circling a particular region, after few minutes some new satellite comes. Okay, so this advantage we are using by using relay fetch. We are utilizing this advantage. Okay, so this first in orbit CDN, a novel architecture that places caching logic directly into the LEO constellation, and satellite NAV design, which is addresses orbital motion, ISL topology, and cache coherence. So this challenge is obviously unique to space infrastructure, and the proven performance we have already seen by the results of the simulation. So 2.5 times latency reduction and up to 80% of bandwidth saving, that has validated the full constellation at scale. And if we talk about the future infrastructure, so as LEO constellation scales to tens of thousands of satellite, so this in orbit CDN becomes the foundational internet infrastructure for future. And one small thing that I want to add is that why you are more interested in the satellite technology or the satellite internet, because still in this world there are many remote places, maybe some islands, or in this world like in the Antarctica space or the Greenland space, there are many areas where the because of the obviously the climate and the topology of the mountains, oceans, and all. So this building the cell towers is not possible by, so this wireless network is not possible by using the cell tower or this kind of electromagnetic waves. So for those kind of places we have to use this internet technology, and as far as I know, this Starlink has already came into action and already serving millions of users, but in India this service is not available till now. Hopefully in future this service will be available on India also. Yeah, so I feel that this satellite internet is a very great place for research, because in future maybe everything may shift to the satellite internet if we can increase the bandwidth problem. If we solve the bandwidth issue, then I think this a lot of wire technology, like lot of installing cell towers, installing laying out the lanes or laying out the wires. So actually these all things come with a very high cost. So if we can actually put the internet to space, then it solves two purposes. So the first one is that the cost will get decreased, because this installing towers, installing the wires overseas or the overground, so this cost will get reduced, and also this satellite will give the global connectivity, like anywhere. So from anywhere in earth we will be able to access the internet. Okay, so by utilizing the satellite, we are achieving the cost also, like reducing the cost and also increasing the availability of internet. So I feel that this will be a great space for research in the upcoming years. So thank you so much for watching the presentation. I hope you liked it, enjoyed it. Thank you so much.